Okay, today we are going to continue talking about the inverses of matrices. So from last time, in the 2 by 2 case, there is a convenient formula. So if A is a 2 by 2 matrix with entries A, B, C, D, then the inverse is given by this formula here. So you flip the diagonal terms, add negatives on the off diagonal terms, and then divide every entry by the determinant, which is this combination here. Let's do an example. Let's take A to be the matrix 1, 5, 2, and 7. Okay. Then to find, and so the question is to find the inverse. And okay, we'll just simply use this formula. A inverse is 1 over the determinant, and you switch the diagonal terms and stick minus signs or negative signs on the off diagonal terms. Now to compute the determinant, what you do is you multiply the diagonal terms, the A and the D, which in this case are 1 and 7. So that's 1 times 7, and then subtract off the off diagonal terms, the 2 and the 5, so their product. So this is 7 minus 10, or negative 3. Okay, and so this becomes 1 over negative 3 times the matrix that we have. And this is, remember scalar multiplication, you take your scalar and multiply every single entry of the matrix by it. In this case, we're going to be dividing by negative 3. And so this matrix becomes negative 7 thirds, 5 thirds, 2 thirds, and 1 third. Okay. Now, so this is our answer. This is the inverse of this matrix A. And we wouldn't have to normally do more work. But I want to show you that, for example, A times A inverse is indeed the identity matrix by doing the matrix multiplication. And so, okay, A is 1, 5, 2, 7, and then A inverse is negative 7 thirds, 5 thirds, 2 thirds, and 1 third. And so we've got a 2 by 2 matrix here. We're multiplying by a 2 by 2 matrix here. So we can certainly, we're allowed to multiply them because these two numbers match up. And then the answer that we're going to get will be a 2 by 2 matrix. So it's going to be I'm going to put a 2 by 2 matrix here. I've drawn it so big because you'll see in a second. All right, so the term in this 1, 1 position is row 1 times column 1. Not times, but I mean dot product. So 1 times negative 7 fifths, 7 thirds, plus 5 times 2 thirds. So here's the 1, I multiply by the negative 7 thirds, and I take this 5, multiply by this 2 thirds. Again, row 1 dotted with column 1. And if I simplify the arithmetic here, negative 7 thirds plus 10 thirds is exactly 1. Now I'm going to figure out what goes in this position. This is the row 1 column 2 position. So I take row 1 dot product with column 2, and so I'm going to take 1 times 5 thirds plus 5 times negative 1 thirds. 1 times 5 thirds plus 5 times negative 1 third. And when I do the arithmetic there, it does become 0. Finally, well, not finally, but in this position, this is row 2, column 1. Here's row 2, there's column 1, and so I'm going to do 2 times negative 7 thirds plus 7 times 2 thirds. When I do the arithmetic there, it's indeed a 0. And then finally, row 2, column 2. Here's row 2 of a first matrix, column 2 of a second matrix. And so what I have to multiply is the 2 and the 5/3. That's 2 times 5/3. And then add to that 7 times negative 1/3. And that becomes 10 over 3 minus 7 over 3. So sorry about that, 1. Okay, and so this here is the 2 by 2 identity matrix, and we've verified that A times A inverse is the 2 by 2 identity matrix. It's also true that A inverse times A is also the 2 by 2 identity matrix, but I won't do the computation. It's very similar to the one we just did. The next question is, well, what good is knowing A inverse? And the answer is it can help you solve systems of equations. So on the next slide, okay, suppose we were given this system of equations. We've got two equations, two variables, x and y, and we want to find what x and y are. So what we do is turn these coefficients 3, 1, 5, 2, put them in a matrix, put the variables in a 2 by 1 matrix, and the way we define matrix multiplication is of these two matrices is so that we get these equations when we multiply this 2 by 2 and this 2 by 1 matrix together. And the answer will be a 2 by 1 matrix, and we want that 2 by 1 matrix to equal what's on the right hand side here, namely this 2 by 1 matrix consisting of 7 and 12. So if we let boldface letters denote this 2 by 2 matrix A, boldface X denote this 2 by 1 matrix of variables, and boldface B denote this column vector is what it's sometimes called, then our equation, or system of equations, two equations there, becomes this matrix equation here. So it's a single equation. A times X equals B. And here's now where the inverse matrix comes in. We multiply this equation, both sides of it, by A inverse. So here I've multiplied A inverse on the left, A inverse on the right, and what happens is the A inverse times this A, they cancel, and we're left with I. Here's I sub 2, the 2 by 2 identity matrix, and here's just A inverse of B. Now, when you do the matrix multiplication of the identity matrix with this matrix labeled X, it turns out you can check that you just get X. So we've solved for X, namely, it's A inverse times B. So going back to our example, we have to find A inverse. And then using the formula on the previous page, we find that A inverse is given by this. This particular A is different from the one we had on the previous slide, but anyway, you basically flip the diagonal entries and put a minus sign on the off diagonal entries, as we did last time. And all right, so then here's our A inverse, here's our B, and then we just do the matrix multiplication. So we're going to expect a 2 by 1 matrix. So here I've made a 2 by 1 matrix, and in the row 1, column 1 position, I take row 1, column 1, dot them, 2 times 7 plus negative 1 times 12, and then this place here is row 2, column 1, row 2 dotted with column 1, negative 5 times 7, 3 times 12, add them. And once you do the arithmetic, you get 2 and 1, and so that's what our X is. Remember, X was this vertical vector of X and Y, and so X is equal to 2, Y is equal to 1 is our solutions to the system of equations. So we no longer have to do row reduction or doing a bunch of algebra. We just have to compute the inverse of a matrix in order to find the system of, the solutions.